if you are not comfortable in any way by dealing with electrics and electronics, have a qualified electrician do this for you. If you screw up, damage to property, serious injury, or death can occur. Hi guys, welcome back to Lupus Custom Knives. So this is part 5 of building our heat treatment oven, and today we'll be talking about the mathematics and calculations we need to undertake in order to properly design our oven. So without wasting any more time, let's get straight to it. Not a lot of tools we need today, really, just a pen, some paper, and a calculator. Okay, this might come in useful, but we're gonna have a look. So the first things we need to be concerning ourselves with is the dimensions of the inside of our oven, precisely the chamber. Okay, now I know full well that the length of my chamber is 44 centimeters long, or 440 millimeters. I know that the height is 125 mils, and I do know that the width will be 130 millimeters. Okay, the first thing we need to figure out is the surface area of the firing chamber, of the hotbed, effectively. And for that we just need to add up the square areas of all the walls together. So let's make it easy. We know full well that we've got two walls that are 440 by 125, which are the side walls. Okay, we know full well as well that we've got two walls of 440 by 130, which is the top and bottom bits, and we've got two walls of 125 by 130, which is our back and our door. Okay, so if we multiply everything and add everything together, we'll end up with okay, one thing I do have to tell you, you want to be using square centimeters for this, but however, this being the metric system, all you need to do to convert it into centimeters is just add a decimal. Okay, so let's just do that real quick. So for 40, there we go, and that is the surface area of the inside of my chamber. Okay, now what we are concerned with is something called surface loading. Okay, and sometimes it's also called power density. As a matter of fact, I do prefer the term power density, and why? I'll tell you why in a minute. Okay, so power density, let's call it PD. Okay, now power density is measured in watts per square centimeter. Okay, so obviously that is power divided by the surface area. Okay, now we've got our surface area. What we're concerned with at the moment is the power, because that's what we are trying to figure out. We need to know how powerful to make our oven. But we have another unknown in the equation. We don't know what our PD is. Now PD is a constant, and you sort of have to establish for yourself what it's going to be. Okay, as a rough rule of thumb, your PD should be larger or equal to 0.8. Okay, a lot of commercially available ovens and kilns use give or take 0.8. Some of them use even less. If your PD is less than 0.8, your oven will take a while to heat up. Okay, it can take quite a long time. If your PD is very high, by very high I mean over 1.4 and 1.5 and higher than that, your oven can actually be overpowered and struggle to keep temperature, because the moment it turns on the elements, it just overshoots by a huge amount. Okay, so a good guesstimate to aim for is 0.8 to 1. Okay, that's at least what I'm aiming for. Your mileage may vary. So we know that let's use this example. We want our PD to be 0.8, okay? So now we can extrapolate this for the power, which is going to be PD multiplied by surface area, which is 0.8 multiplied by 2569, which equals, so the previous answer multiplied by 0.8, which gives me a very interesting answer that I don't understand, but there we go, gives me 2055. Let's round it up, okay, 2055 watts. So if I want my power density to be 0.8, I'm looking at my power elements, the heating elements, being about 2 kilowatts or 2000 watts in power. Okay, so this is what I want to be working with. So now that we've got that established, let's put this sheet aside, because we'll be referring to it a bit later. Other things we have to know is we need to know what's called the Ohm's law. And Mr. Ohm found out a long time ago that current, or I, is equal to voltage, or V, divided by resistance. Now, the power supply that my oven is going to be running on is a regular single-phase household supply, okay? Your box standard variety. We should know that they can take a maximum current of 13 amps. If you live somewhere else than the UK, yours may be different, okay? So double check. Now, and we need to know the voltage as well. And I measured this particular socket because that's where I'm going to be connecting my kiln into. And that voltage comes up as 243 volts. Another thing we need to know is how to calculate for power. So power is simply current multiplied by voltage. And that, in our case, the maximum power we can draw from that socket is, of course, 13 times 243, which is 3,159 watts, just over 3 kilowatts, okay? That is, over here, the absolute maximum I can pull through this particular socket without blowing any fuses. However, there are things to consider. Let me give you a quick rundown, okay? The cable, before it comes here, it goes through my other shed that I showed you when we were drilling some aluminium, and it splits in there into several power sockets and several light switches. Then it comes here. It's split into 6 power sockets. Of course, they are never on at the same time. They are just placed evenly spaced for convenience. And it's running 3 fluorescent lights. So I will never be able to run this power, okay? Because I'll be overstressing my cables, if you like. So we need to be aiming for something lower. Now, how lower you are aiming for is up to you, okay? But I want my power maximum to be no more than 2500 watts, okay? This is my hard limit that I've set for myself. Now, if you've got a 3-phase supply, or if you've got more heavy-duty sockets or anything else, your figures change. Okay, this is an example for my particular case. So let's make sure that we have that clear. Okay. So now that we know this, and we know how powerful we need our elements to be, we can go ahead and we can design our elements. Now, for the moment, I will presume that you are actually calling up a company that does this, and you are telling them what sort of specifications you need your elements to be. Okay, so let's say they arrive, and you measure them and everything else. So the one thing you want to measure on the both power elements that you receive is their resistance. Okay, and I did that, and my resistance came up to be 26.5 ohms. Okay. So, looking at this formula over here, we can see that power is current times voltage. We also know that the current is voltage over resistance. So power is really voltage over resistance times voltage, or voltage squared over resistance. You with me? Okay, so now I have my resistance and I have my voltage, which is right there. I can figure this out, how powerful my elements really are, which is 243 squared over 26.5. Let's figure this one out. Two thousand 2,228 watts. So this is the actual power of my elements. As you can see, it is higher than what I originally planned for. But that's probably better. For entertainment's sake, let's just figure out what our PD is. So that is, let's have a look. Okay, of course it's watts divided by square centimeters. So we have 2228 divided by, where's our square area? There we go. 2569 equals. So P D actual will be 0.867 watts per square centimeter. Now, of course, that is higher than 0.8 that we originally set our goals at, so we are very happy. Okay, so all of this was true if you are buying the elements pre-made. But what if you have no other choice but to wind the elements yourself? Well, you'll be needing to do a lot more calculations than this. Okay, so let's put this aside and let's rest it there. So let's go back to our original example. Okay, so you figured out how powerful you want your elements to be. Okay, you did the math, everything comes up right, and you decide you want them to be. Let's round this up. Let's say you want your power to be 2,000 for just nice round numbers. Okay, and let me just write on this: if you are winding the elements yourself. Okay, so we have P, which is 2,000 watts. What you want to be figuring out now is how much resistance your element has to have. Okay, to put in simple terms, how long does it have to be? But we're going to work on that. So we did know from the previous sheet we've made that power is equal to voltage squared, that's supposed to be, over resistance. Okay? The thing we are concerned with from over here is resistance. So if you multiply everything by resistance, just to work things out, we're going to end up that P times R is equal to V squared, or in other words, resistance is equal to V squared over power. Then let's work this out real quick. So 243 squared over 2,000, which is the one we had right there. Let's find this out. 243 squared divided by 2,000. 29.5. Let's round this up. Ohms. Okay, so this is how powerful your this is how much resistance your wire has to have. Now, when you are buying your wire, the manufacturer's website or the dealer's or retailer's website should list you a property such called resistance per linear meter. Okay, so resistance per meter, RPM in our case. And let's presume that I don't have any data on me right away, so I'm just gonna pull a number out of my head. I think 0.57 ohms per meter is a reasonable approximate to what you may be encountering. Okay, 0.57, we'll work with that. So now you need to know is how long your element needs to be. Okay, so all you need to do is you figure out the length, which is going to be your resistance total that you found out, which is this, over the resistance per meter, which is that. So if we have 29.5 ohms and we divide those by 0.57 ohms per meter, we'll find that 29.5 divided by 0.57, it is 51 point, let's round it up to 51.8 meters. This is how long your wire has to be in order to have this resistance, in order to have this power at that voltage. Okay, see how everything sort of ties in together? The smart thing you can do is you can actually make an Excel file. If you are computer literate, you can make an Excel file with all these interlinked to one another, so you can use formulas, and afterwards you can just change the input parameters on all the data updates for you, so you don't have to redo all the calculations if you just change one bit. And you know, that's what I did, and it makes life a whole lot easier. I did actually think about winding the elements myself, just because I like to be doing things myself, but I realized in my case it just wasn't worth it. Okay, so but you know, your situation may be different. So we've got that. Now what we need to find out, another important thing, and that is what is called, once again, surface loading. That's why I preferred to call this over here power density. Okay, so the two don't get confused. Now, what surface loading is, it is, I'll use this, call this SL, surface load. It's measured in exactly the same units, watts per square centimeter. Alright, now, watts per square centimeter, however, this time we are talking about the actual wire and not the bricks. This is not the inside of your oven. Let me explain why this is important. This is also the reason why in the previous video I did tell you not to get the cheap heating elements from China and Hong Kong you find on eBay. Is because their surface loading is really, really high. Now, what surface loading is effectively how many watts you are, or power, how much power you are pumping out of a set section of wire or square area. So we need to what we'll need to be figuring out is what is the surface area of our wire. That's going to be quite easy. Now, when you are looking for wire to buy, for it to have 29.5 ohms of resistance, for example, you will find a load of different thicknesses. Okay, and different thicknesses are going to have different resistance per meter. So pick one, start working with it. If it doesn't work out, use another one. Okay, so trial and error, that's where the Excel sheet comes in real handy. So let's give this a try. So let's say that our wire is, let's use a diameter over here, is, let's say 1.6 millimeter diameter. Okay, but because we're going to be using square centimeters, let's just make sure that we are using proper units, and that will be 0.16 centimeters. Oh, not squared, just regular centimeters. Okay, that's our diameter of the wire. Now, we also need to know the length of the wire, but we have already figured this one out. Okay, the length is 51.8 meters, or, in other words, 5,180 centimeters. Okay, because there's 100 centimeters per meter, so we move it as 2 places across. Okay, ignore that. This is take 3 of something I'm trying to explain. You'll just continuously screw up. Okay, first thing you need to figure out is the length of your circle that your wire does. Okay, if you imagine this being your wire multiplied 1,000,000 times, you need to figure out this length around here, and it's quite easy. Of course, the formula for this length of a circle is 2 pi r, but since we have a diameter instead of radius, it's just simply pi d, in which in our case, let's just call this w, okay, so we don't get confused. So pi d, which was going to be, where's my pi? There we go, shift pi multiplied by 0.16, 0.502 centimeters. Okay, make any sense? Now, the surface area of the whole wire will be the length of that wire circle, which is that, multiplied by the length of the wire, which is L. That's a rubbish L, not an E, okay? Which is 0.502 multiplied by 5180, okay, which is almost precisely half 5180. 2603.75 centimeters squared. Okay, and now to figure out the surface loading, it is quite easy, because that is simply the watts which we have, which was 2000 divided by 260. Let's round up to 4. Okay, so 2000 divided by 2604, which is 0.768 watts per square centimeter. Now, whether that is good or bad, I haven't got a clue. You have to look up on the manufacturer's website to find out what they recommend for the surface loading. What I do know is that surface loading changes depending on temperature, which is pretty much common sense. The higher you go, the lower your surface loading must be to make sure that the wire survives. Okay, the hotter it is, the more easier it is to burn out, and as such, the surface loading must be lower. If I am correct, and it's a possibility that I'm not, I think that for Cantle A1 wire, which is what your heating element should be made from, a acceptable surface loading is approximately 2.4. So we are well under that. Okay, we are well under that. A couple of things you can do at this point. You could either go to a smaller diameter wire, okay, which is going to have a different resistance squared per meter, which in turn is going to change your length, which in turn is going to change both the length of the circle and the length of the wire, which is going to change the surface loading and maybe bring it closer to 2.4. It's up to you. If you want something that is really fail-safe and you don't want it to fail, you want this to be as low as possible, okay? And here's the difference between the two. In power density, you really want it to be quite high. Not as high as possible, but you want it to be within reason, as high as possible, with limits. This one you want it to be as low as possible, also with limits. There's no need to go for the very, very thick wires to make your kiln from, because, well, we will not be running the powers in here that would warrant something like this. Okay, other things you have to consider: if you are winding the elements yourself, you've got to consider the mandrel size around which you're going to be winding your wires. This will influence two different things. First, it will of course influence the diameter of the spiral once you're finished with it, and it will influence the number of coils that are going around it, thus influencing the whole length of the spiral. Don't forget, once you are done with your spiral, you have to stretch it to anywhere from 2 to 3 times its original length to make sure that the the coils themselves don't touch one another and don't short circuit the whole thing. My advice again is, if you can, get your heating elements pre-made. Okay, the guys who are usually selling the wires are usually the ones who wind the elements anyway. And it's probably just less of a headache for yourself, because they've got all the equipment for it, and they are geared up to do it, and they probably have all the programs on their computers that will tell you all this at a blink of an eye. Okay, it's probably just easier that way. But if you can't, if you're stuck, then you can always fall back on something like this. Much like with everything else on this channel, you are invited and you are expected to check everything for yourself. Okay, none of this is to be taken as granted. I could be completely wrong with several things. I don't think I am, but I could be. So it is for your best interest to double check any maths before you apply them to your own situation. So that's it, guys, for this video, and I hope it's a bit clearer and it's not so much of a witchcraft now on how to work out how powerful your kiln needs to be and all the other parameters of it. In the next video we will be going through the schematics of everything, okay, making sure to demystify that a little bit, as well as what connects where, how and why. But for the moment, thank you very much for watching, have a lovely day and take care.